Okay, thank you very much for the introduction. And today I will talk about a joint work with Ismael Bailleul. And the idea was to consider singular stochastic PDEs where actually you have some locality in the sense that you no longer have translation invariants and you work with kernels which are no longer radial, and then you need to be a bit cautious. And the idea was to see what, when you apply relative structures to these singular SPDEs, what actually you can recover if the general framework works and if it needs some adaptations. And it was also for us an opportunity to revisit one of the main proofs of the theory for writing up the renormalized equations. And in this work, we provided a simpler proof, even in the case of non-translation invariant case, which is new in comparison to the literature. So I think we can move to the next slide. Okay, so just to put the framework. So what I mean by non-translation invariant SPDEs. So here for simplicity, I will just take X in the torus, but it could be on the D-dimensional torus for just notation simplicity. So that's a point, so with a typical spacetime point. And then we will consider operators, which are of the following form. So that, okay, here I just put the Laplacian plus a derivative in space. And you imagine that now you have some coefficients in front of these operators. And these coefficients depend on the space-time points. So in the translation invariant case, it will not depend on the space-time points. And you suppose also that these coefficients are smooth. And now we consider a system of parabolic equations of the form below. So I have k0 unknown, so this ui. And these equations are the form like KPZ type equations. So with a multiplicative terms, multiplicative noise. So we may think like one typical example would be the generalized KPZ equations. So for instance, I have f of ui times xi, which would be a n0 dimensional spacetime noise. And then I have some nonlinearity gi depending on u and first derivative of u in space. So if you want this type of system is a prototype of singular SPDEs that you want to consider with a general framework. Just to mention for those not specialists, in the sense that the singularity comes from the noise, the xi, which is a distribution. And often when you do some scaling argument, you can see that u is not differentiable. So in fact, dxu, it's a distribution. So there are some products here that will be ill-defined. So before explaining roughly how you solve these equations using relative structures, I want to give you a brief recap of what has been done in the literature and what were the approaches for these equations. So I think we can move to slide 3. Okay, so let's mention when AI and the PIs are constants, relative structure can solve the system, like give you local watpotness local in time. So this is a compilation of 4 works. So the first one for Martinera introducing relative structures. Then the second work is about the algebraic renormalizations of relative structures. And then you have the convergence theorem in the third paper, which is this from AJ Sandra and Martinera. And the last paper, which is in collaboration with Ilya Chivarev, AJ Sandra, and Martinera. Here we provide a writing of the renormalized equations. Because what happened is that you need to you smooth out your noise, and then because you have some ill-defined products, you have to put some renormalization constants in your equations. Okay, let's mention here that if the coefficients are non-constant, which is our framework, this has been considered by parallel control calculus, but not at the point of generality that you can see in relative structures. So here I mentioned the foundation work on parallel control calculus. And it's mostly done in some works, follow-up works from Ismael Bailleul and some co-authors. And what are the main motivations for considering these SPDEs? I mean, these SPDEs could be seen as an intermediate step from defining SPDEs on a manifold in a systematic way. So here I mentioned a work in progress of Martinera and Singh. And if you want, our work lies in between, like the invariant case and when you will have to work on the manifold, because here there will be some geometric setting, and we are not considering geometric setting here in our work. Okay, so I think we can move on to slide 4. Okay, just last to mention that what are the main features of the theory? I mean, you already got some insights previously in the week, but just let me recap briefly. So here you consider a generalized KPZ equation, which is given by this dtu dxu squared fu times dxu squared plus g of u times psi. And by some scaling argument, you can just realize that actually the regularity of u is governed by the regularity of v, which is given as a solution of the linear equation. So dtv equal dx Laplacian of v plus your spacetime one noise. And one of the idea in this type of expansions that you can perform on these singular SPDEs is to look at u a solution where you have a specific expansion. And in fact, you hope that all the singularity or the fact that u, for instance, is not differentiable comes from the fact that in the expansion would be based on v. So we have this type of expansion, u equal v plus w, where w should be a reminder with nicer regularities. Of course, this could work if you have polynomial nonlinearity. You can run this type of expansions and hoping that the regularity is improving, and then on the reminder, you do a fixed point. But if you look here on this general KPZ equation, you have f of u and g of u, which are basically non-polynomial nonlinearity. And for that, you will need to linearize, and the linearization will be local expansions. So instead of doing a global expansions, you will go through a Taylor expansions. So when you Taylor expand the normal monomials will not be enough. You need to have extra terms that will be very good for approximating u. So below you have a sum, so u equal to the sum over tau in some capital T, so it would be a combinatorial, I mean, some abstract space. And then I have some coefficients, theta of x, that should be understood like derivatives, I mean, like generalized derivatives. And then I have my new monomials, which are these u tau x. And my new monomials actually will be recentered, there will be recentered Gaussian stochastic processes. And I have some coefficients, which are these c tau x, which are the Taylor expansions. And I have a reminder that could be understood as some Taylor reminder. So that's the general form. And the way you index these Gaussian stochastic processes, actually, they're like iterated interval built upon the noise, the it kernel associated to your equation, to the kernel associated to your equations. So you have to do convolutions, products, and so on. So here, I just want to present you some terms, or you define these center Gaussian stochastic processes. So maybe Tom, you can press the next slide. Yeah. So these three center stochastic processes, for instance, for the first one, so these are, I mean, you can see here these trees along. So you have u, and the subscript, you have a tree, comma x. And for the first tree here, you see a gray dot with a blue edge. And if you want, the blue edge corresponds to a convolution with the kernel k, with the it kernel, and the gray dots correspond to your noise. So if you want, this is like the solution of the linear equation. And because we want this term to be recentered around x, you need to subtract this value of this stochastic interval at the point x. And then immediately on the right, I just show you what actually are the recentering for classical monomials. And below, you have a more sophisticated term where you have this tree, you start with a blue edge, and then you have two brown edges. The brown edges are for dxk, so the partial derivative of your it kernel k. And so you have a squared dxk convolution with your noise square, and then you take the convolution again with your it kernel. And also in that case, it just boils down to subtract the value of the process at the point x, and this gives you like a recentered iterated interval. Okay, let's mention here that, of course, you need to construct these objects. I mean, there are some renormalization going on behind the curtain, in the sense that these objects they are well defined if you modify the noise. And if you want to define them in the probabilistic meaning, the limit, you need to act with some renormalizations. And also for the recentering procedure, could be quite involved. Here, I'm just subtracting one term, but you may have to subtract several terms if you have like a bigger iterative interval. So this is really the general flavor of the theory, to have these three expansions or iterative interval which have been recentered around the point X. I think we can move to the next slide or press the button. Yeah. Okay. Let's mention. Okay. So now I have this general black box. So I know that I have some Taylor expansion of my solution using iterative intervals. And these iterative intervals, I form what we call the model. And we have to renormalize this model and then to show that it converges, it has a limit. And when you do that, because you put some renormalizations on this iterative interval, actually you will change the equations. So the original equation you start with need to be modified, and you need to add these renormalization constants. So here I just remind you what are the main steps if you want to move from non-local to local equations. So there is one step that I will not touch upon, that I will just mention here. There is basically an analytical step, because you are using kernels and you are using estimates on your kernels, and you are now you have no radial kernel. So here, basically what you do is a straightforward adaptation or like use of the formalism given in this survey, nice survey by Ismael Bailleul and Masato Shino, a tourist guide for relative structures. So all the analytic part connected to relative structure could be actually extended to using this framework. Okay, then if you want to define the model, like this recenter interval that I presented, imagine that you have smoothed out the noise, so no renormalization is needed, then it is completely identical to the original constructions. You don't need to do any modifications. Then the third step will be actually to try to renormalize this iterative interval. And that step, of course, there will be some change because you lose translation invariance, you expect to replace constants, renormalization constants, by functions. So these are like the main change. The fourth step, I would say that the convergence of the renormalized model is relatively open right now. I mean, maybe you can work out it in some specific case, but for trying to adapt this general theorem from AJ Sandra and Martin Herrera, for the moment, it's not done. It's completely open. And then you have the last step, is that once you have renormalized your iterative interval, you want to write up the renormalized equation for your solution. And actually, this is the main result that we obtain with Ismael Bailleul, that you are able to write up the renormalized equations, although we didn't prove the convergence of the renormalized model. So then I would like to move to the next slide where actually I present the main results. Yeah. So that's the main result that we obtained with Ismael Bailleul, is that we know that when you do these Taylor expansions on trees, or like you just actually focus on the finite vector space, you have just a finite number of trees. And actually, we define for a certain category of maps or renormalization maps that are maps given by the name R. So that maps depends on the spacetime points, and they go from your abstract space T into T. So if you want, this is like computing the renormalizations by putting functions instead of constants, renormalization constants, and you have some counter terms which are in T. And we call this map strong preparation map. So I will explain in a bit what is the definition. So this is a terminology that we use, but there are also other terminology in the literature. I mean, strong preparation maps were known before, but strong preparation maps it's a new notion. And then when you act with this map on your iterative interval, actually you can write up the renormalized equations, where actually you have like so the first part of the equation, so it's just the equation without renormalization, and then you have a term which actually put the renormalizations, and the renormalizations, okay, they appear here on some noises, which are on some noises, and what you have here, this is R star, so this is like in the dual. So basically you act on you have the dual map of R that will act on an abstract version of the noises, which are this zeta L. And this gives you like the contra terms. And if you want this Fi tau U dxu is what will be used in numerical analysis when you do a numerical scheme that will be called elementary differential, the elementary differential. So these are the coefficients that you got in your numerical scheme. So this is completely explicit. Once you know the map R, and you can compute the adjoint, this R star, and you apply it on your abstract version of the noise, and then you can compute this coefficient and give you the contour terms. Okay, for those who know have some background, when I write this R, actually you can recover BPH renormalizations. It's just generalizations that cover BPH renormalizations. And if you want the BPH renormalizations that we obtain for renormalizing SPDES, it's just a sub-result of this theorem. So now in the next slide, I would like to explain actually what are the properties, or what is this map R? What are the main algebraic properties that you need to require on this map R? And then I would like to do, or I to sketch a one-page proof of these results, or like if you want one slide proof of these results. Okay, I think we can move. Okay. So then I just put some context. I mean, or what are the, when you do these iterated integrals, what are the main algebraic or combinatorial objects that you use? So what we are using is called decorated trees. So there are rooted trees. And then you put several decorations on the edges and on the nodes. So I presented some of them in the example. So for instance, on the edges, you can encode kernels, noises, derivatives, and decorations on the nodes will be for polynomials, monomials. And if you want below, you can see example of trees, decorated trees. So here I put decorations, like Latin letter on the edges. So they could be in a suitable space for encoding these kernels, derivatives. And on the node, I put Greek letters. And also what is useful, you have this abstract operator, this calligraphic I subscript A. This could be seen as an abstract integrator or an abstract convolutions, because if you interpret this tree, it would be a convolution with some kernel. And you just take a dot or a tree and just connect that tree to a new root with an edge decorated by A. So this would be actually the equivalent of the B plus, which is used for the Connes-Kreimer coproduct. This is the type of operator that we use for constructing this tree. And as I say, that you want your expansions to be finite. You don't want to deal with infinite expansions. So we consider a finite dimensional space of decorated trees T, that are generated by the equation, in the sense that you run your perturbative expansion, then you produce a bunch of trees. And the way you construct the tree are constrained by the product that you see in your equations. And then there are like two numbers, or like you want to measure the size of your trees. The first measurement would be the number of noise symbols. So this is like for probabilistic, and when you do some probabilistic arguments by counting the number of noises connected to the Wiener-Cloud decomposition in the Gaussian case. So basically it tells you that your terms are simpler or like smaller. And then the second point, the second element that you want to keep track of is that you will have a degree map, which will be a map from your trees into R, and that will associate to a tree a number. And this number basically tells you if the tree is singular or not. You always like the number that, and it's like a power counting for Feynman diagrams. So for instance, you can, if the number is negative, then the regularity of the tree will be a distribution. So there are this type of the measurement that you have. So two measurements, so like the number of noises and the degree of the term. So then we can move to the next slide. Okay. So then, okay, so you have, we see, okay, here I will define a Connes-Kreimer coproduct or Connes-Kreimer type coproduct, because it is slightly different, but actually very similar. And in fact, I will consider the dual. So I will consider a product on the trees given by this circle, this O dot. And instead of giving you a formal definition, I just wanted to illustrate this product on two trees. So here I've omitted like the decorations on the nodes because they're completely, you don't need decoration on the node at this stage. So here you just see decoration of the edges. And what happened, is that I have a tree here on the left and another tree on the right. And when I try to plug that tree or the branch of that tree onto the other tree. So for instance, the first tree, I've decided to plug tree BC here on the node, on the root of the tree where the edge is decorated by A. Then on the second tree, I've decided to plug the tree on the nodes upward, so not the root would be upward. And then the other two trees, I decided to plug one branch decorated by B on the root and the other branch decorated by C on the top node. And then I reverse, I put C on the root and the edge decorated by B on the top node. So this could be seen as a Connes-Kreimer, where actually you don't cut edges. So you just, the number of edges is preserved by this product, by the coproduct. So you don't cut these edges because the edges carry decorations. So you don't want, if you cut edges, you lose this information. So you don't cut edges. And I said, in fact, you can see this product as a dual, some variant of the Connes-Kreimer coproduct. So I think we can move to the next slide. Okay. So why I'm talking about this coproduct is that because actually you can look at some deformed version. So this is like a perspective that we developed 1 year ago with Dominique Manchon. Like actually you can deform the product, the O-dot product, and then you get a product where actually you play with decorations. So basically on the shape is exactly the same operations, but now I can play with decorations. So all it works. So here I have a tree and so this will be denoted by the star product. So I just focus on the first term where actually I plug the tree BC on the root. So what I can do then, I can subtract decorations on B and subtract decoration on C by L1 and L2. And if I do that, I need also to subtract these decorations on the root. And so it's given by a sum, and so and the L is taken over omega, so it will be L1, L2. And I can also, I have some delta here at the root. And I can also put this delta on the two nodes, so I can put on the nodes decorated by alpha or on the root node. So here I will add delta 1, and here below I add delta 2. So if you want, this is just, you can rewrite actually this product here, the star product, as the other product plus terms of lower orders. By terms of lower orders, I mean that you will measure the size of the tree by taking the sum over all the decorations. And then you see here that by playing these decorations, actually the decorations are decreasing. So you have minus L1, minus L2. So actually only for L1 equal L2 equals 0, this will be the term of higher order. And then the rest is decreasing. And in fact, also you can see it as some deformation. So in certain sense, it's not immediate. One needs to work. It would be a dual of some coproduct that can be seen as a deformation of the Connes-Kreimer coproduct. So why I'm presenting this product star? Because this is like the key product that actually we use in the sequel for renormalizing our equations. So maybe we can move. Yeah. So now I'm coming to this preparations map or strong preparation maps. So first, the definition of a preparation map. Here I give it in the translation-invariant setting. So there's no dependency on the space-time point. But if you move to non-translation invariant, you just add the dependency on the space-time invariant on the space-time point. So a preparation map.
Sorry, is it me who has lost connection?
No, it's Yvain.
Hi, Tom. We're still here.
Okay, but Yvain is not cannot be here, right?
Nope. All right, we will join again in a minute.
It seems he's not online.
Okay, so I got some connection problems, so I have to switch from the hotel to my phone. Okay, so I continue here. So you have this definition of a preparation map, and then what is crucial is that you have this identity below that if you look at the dual of the adjoint of that map, then you have some morphism property for the star product, which is this deformed Connes-Kreimer coproduct. And what we ask here is that this map R star is a right morphism. And this will be a right morphism for sigma for tau in capital T and sigma in capital T plus. So I put a plus here to just stress that it will be trees of degree, positive degree, so that all the outgoing branches, outgoing the roots, there will be of positive degree. And you say that it is a strong preparation maps. It's actually, it works, the identity one works for every sigma tau in capital T. So in this sense, it's stronger because T plus is smaller, it would be smaller than capital T. So these are the definitions. And if you work with this renormalization map, with this R map, actually the strong preparation map, it's enough for renormalizing the equations. So maybe I move to the next slide to give you, yeah, so maybe one example. So one main example of preparation maps are the map used for BPHS renormalizations. So, well, the way you construct them looks quite simple. Because you need this right morphism property, actually you construct the adjoint using the star product. And you have like a sum over sigma and T minus, which are 3 of negative degrees. And then you take the convolution with stars of tau with sigma. So if you want T minus are 3's of negative degree, L will be a character from T minus into R, so a character on the forest generated by the negative trees. And here, this character has this expression, so expressions, and will be given by this expectation. So here will be this expression will be only valid in the invariant in the translation invariant case. And we have some map, recursive map, pi RL, which is what we call the renormalized smooth model that interprets this tau as iterated interval. And then you have S sigma, which is a symmetry factor of the 3 sigma below L sigma. So this is your normalization map, and this actually encodes the BPSS renormalizations that we use for renormalizing these stochastic iterated intervals. And I'd say that this definition that I write here, I mean, just if you put a base point, like it is completely robust. It works the same. Okay, maybe we can try to move on. Yeah. Okay, so now what I have, okay, I have some preparation map or strong preparation maps, and now I want to construct the renormalization maps out of it. Because if you want these preparation maps or strong preparation maps, what they do is just renormalize a product as a root. So that's the only thing that you renormalize. And if you have deeper iterated interval, you may want to do renormalization elsewhere in your iterated intervals. So you need to basically iterate this formalism. So the correct, I mean, the natural way to see, what was the natural way to see BPHS renormalizations, it was to define directly the renormalization map without any intermediate step as some kind of multi-polymorphism for the star product. So basically, you have M, a map from T into T, and you look at the adjoint, and then you will be a morphism product for the star product. And you can be a bit, actually, you just need to satisfy these two identities. So the first identity gives you the fact that actually this will be a multi-polymorphism. And the second identity tells you that actually you behave well when you try to insert decorations onto a tree. And this characterizes uniquely M star to defining this way. So as I said, you have examples of this formalism for BPH renormalization map, translation maps for instance, Brown trough paths. This was the way to define these renormalization maps. And here I mentioned that this formalism is not robust. I mean, if you try to make it depends on some space-time points, this is not robust because M is performing renormalization everywhere in your iterating intervals. So if you try to renormalize by functions deeper and also as a root, then it's different points. So this you cannot do globally. So then the other way to define renormalization map is to use these preparation maps. And this would be like some kind of recursive procedure where I have some MR defined from a multiplicative map that I've denoted MR times to the power times. And then I compose with capital R. And so if you want R, it's like renormalizing a product as a root. And then with the MR multiplicative, I can go deeper. So you see that MR multiplicative commute with the abstract integrator and you apply again R on tau, and then you apply this multiplicative map again. So this is a different perspectives. And to say that preparation maps and multi-polymorphism coincide, it's an open question. That's true for rough paths. So if you try to define renormalization using these two different approaches, they coincide. It's a very nice result. But for related structure, it's not clear. It's an open question. So maybe we can move to the next slide. Just how much I have, Peter, because I don't have the time with me.
Well, we had some bumps in starting. It's usually 40 minutes. So let's say another 5-10 max.
Okay, thanks. So it'll give me enough time to finish the talk. Okay, so now I go back to where you try to how you write or try to prove that you renormalize the equations. So let's mention that when you look at your solution U, actually you try to write the solution first as a t-value solution. So like taking value in this abstract space T. And then by interpreting all these elements in T as iterated integral, basically you recover the Taylor expansions that I presented before. So basically you have some abstract solutions that can be defined as a tree series. So here it's a t-value map. And I have some coefficients, this Fi and some symmetry factor. If you want the coefficient in front of the tree, would be the coefficient that you get in these numerical methods, like the elementary differential. And they are completely explicit. You give me a tree, then I'm able to compute this elementary differential operator. And then there is, this is also what the theory is very powerful, is that I can pick up some UI defined by these abstract expansions. And if I want to plug it into some non-linearity, basically what I do some type of Taylor expansion, which is written below. So I have some lift of straight J into another lift of a smooth function, which is written below. So if I have A, which is an expansion on trees, then I do a Taylor expansion around the point or the coefficient 1. So I have A equal A1 times capital 1, which is the the unit in my abstract space, capital T, plus some remainder A prime. So what I do then, I just Taylor expand, I apply my function on A1, the coefficient in front of 1, and then I have A prime to the power K. And this gives me the way to Taylor expand or my expansions on trees, and I can plug it into some nonlinearity. Maybe we can move on. Yeah. So now, okay, that's very short. But so in the invariant case, we provided with Ilya Chiverev, Ejasandra, and Martin Lehrer, we provided a proof for the renormalized equations. And the paper was actually very long, like more than around 80 pages. And the algebraic argument also were quite involved. And it turns out that if you use this R renormalization map, which are the property of being a right morphism for the star product, actually the proof is very simple. I mean, it's quite, you don't need to use any extended decorations, and the proof is quite straightforward. So for instance, when you try to compute the renormalization, the renormalized equations, basically it boils down to have some dt minus lxi applied to your ui, and then you have some reconstruction map, okay, applied to some tree expansions, which is given by these VIs. So these are just tree expansions of some finite space of trees. I recognize the coefficients, which are this elementary differential operator. And actually, we have an explicit expression for this reconstruction operator. Actually, it's just a multiplicative map, or you can decompose it in two ways. So you apply R, your strong preparation map, on your tree expansions. And then you have a multiplicative map, which is given by this peak XR at. And the only thing you need to know about that map, that it is multiplicative. It is the only thing that we use in the proof. And then when you compute R, your preparation map on your tree tau, on your tree expansions, actually you can rewrite your tree expansion in a nice way, where actually you just have the noise and you have R stars, the adjoint, applied to your noise. So this is some kind of magic identity that makes a proof work. And this is actually where you use all the algebraic properties. So forgetting the last identity of the slides, this is actually where you use the right morphism property of R, and you have also a morphism property for the star product for the coefficient Fi. So once you have written this identity, actually the proof is almost done. But you can really just need to use the fact that the pi at Rx is multiplicative to conclude the proof. Maybe we can move to the next slide. Yeah. So here it's just, and basically this is the proof, okay? So I just rewrite my reconstruction operator. So I have my pi at R applied to Vi. Then the second line, it's just I'm using this nice identity where I can make appear the abstract noise, and I have the adjoint acting on the coefficients. And then I use a third line, I use the multiplicativity of the pi at XR. So it's applied to all my abstract noises. And also it can commute with the coefficients. So it can go inside if you want. And I apply it to my abstract expressions on U. And then I got in the end what I want. So the last term, which is the conclusion of the proof. And what is extremely nice about that proof is that this is really a local proof, because I make appear the renormalization only locally with this R map, which is just a renormalization at the root. And so you can repeat exactly the same proof. And if I put in blue a dependency on X, like R depends on X, then it works the same. So this was something that we noticed after simplifying the proof, that if you put X dependency, it works the same. But if you take the original proof and you try to put X dependency, it doesn't work. I mean, you need to really change the algebraic framework or to extend it deeply in order to get the results. So this was the nicest result what we get trying to work with these preparation maps. And then maybe we can move to some conclusion. Yeah. So just to conclude on this talk is that we provide like a short proof of the renormalized equation that works in the non-translation invariant context. So it was like a huge simplifications instead of now the proof could be self-contained in just 10 pages. And you have some nice, open questions that you have two ways of defining renormalization maps. One using this BPAZ renormalizations, like defined with multiple like you do for branch or path. And you have this recursive way using some R preparation maps, strong preparation maps. And for rough paths, and they are equivalent. But for relative structure, it's an open question. If preparation maps are equivalent to BPAZ renormalization maps, and it's quite hard questions. We don't have the answers. And maybe last final remark is that these are more far from formalism was able to really simplify deeply the proof of the renormalized equations, maybe this could be used for simplifying the convergence theorem for the model, and also to rewrite to prove for the non-translation invariant setting. And also there are some questions around this map R, because this map has any equivalent in a QFT. So this is a question that I addressed to the audience. If this map can have a meaning in QFT. Also, these maps can maybe, I don't know, this map is designed for just renormalizing SPDEs, but this could have been also some interpretations. For instance, if you have some numerical schemes and you want to change your numerical schemes with this R map, I mean, now there are numerical schemes in ODs and PDs using decorated trees. So this R map could also have an interpretation in this context. So I would be very happy to see how one can interpret this map in a different context than the one that can be used here for renormalizing a singular SPDEs. Thank you for your attention.
Thank you, Yvain. And we have a discussion lined up.
Yes, indeed. First question, do you hear me well, or there's quite a lot of background noise, I think, because there's someone speaking in the other office. Do you hear me well?
We hear you well.
Okay, perfect. Good. Then let me share what I have prepared. Okay, you should see my iPad now, my iPad screen.
Yes.
So first, let me thank you, Yvain, for this very nice talk, and also actually for giving me the opportunity to discuss this talk. And what I had thought is because we're such a diverse audience, maybe it would be good to take one step back and explain a little bit how Yvain's how the theory has progressed thus far, which has been very nicely sketched by Yvain. But if I give a little bit more details, then I can actually to say what, in my opinion, the significance of this very nice work by Yvain and Ismael is. So first of all, let me discuss a little bit what is the overview. So I apologize to the experts. This was also mentioned by Yvain, but let me reiterate a little bit. So what is the setting? So we're looking at an SPDE, and we have some second order elliptic operator with for now smooth coefficients. So that's already where one part of the work of Yvain and Ismael steps in, because previously these have all only been constants. So, but let's think of them as smooth. So what is the problem with that equation? Yvain mentioned this very nicely. The noise that runs the equation, which in the general theory, and in particular in Yvain and Ismael's work, it can be a system of equations, and the noise is typically rough, say a space-time wide noise, a space-wide noise, or noises of that sort. And what that means is that by Schauder estimates and power counting, you can see that either the solution U or some derivatives of the solution are actually rough as well. So one can think that they are space-time distributions, as is the noise. And so in turn, what that means is that, of course, then the product that you can see on the right-hand side of the equations, for example, this one, or also possibly this one, is actually ill-defined. And so you want to study a renormalized equation where you have a kind of well-defined notion of product. But so the general question, of course, is from this SPDE, how do you actually figure out what the renormalized equation is, and actually do so in greatest generality? And there has been, of course, a huge body of work, and conclusive answers have been given. So first of all, in the translation-invariant setting, where these coefficients here are actually thought of as constants. And the first very nice and very well, really conclusive answer has been given in this work here. Of course, building on the paper by Yvain, Lorenzo, and Martin, where the algebraic side of the theory has been elaborated upon. And as Yvain mentioned, in the work that he currently presented, namely this one here, together with Ismael, they have given a hugely simplified proof of that result. And now, as a kind of side effect, they realized that by introducing these strong preparation maps, actually they can also deal with the non-translation-invariant setting, which means that you actually are allowed to take some smooth coefficients here. So let me give a little bit more overview of the philosophy. So I think this is to simplify this proof in such a dramatic manner is a huge success. So let me sketch a little bit more the philosophy in more detail, so you can actually see what the significance is. So for now, think of the noise as being smoothed out. This has also been mentioned by Yvain, and think of the coefficients as being constants. And then the first step in this approach, usually you do some sort of formal Picard iteration, and you build this collection of trees according to the nonlinearity that you see on the right-hand side of your equation. So in this case, I wrote it in the very general form that the work of Yvain covers. And then you have these collection of objects, namely trees of that sort, and they really encode products and also ill-defined products. So at this stage, then it's completely, they're just symbols, but they have to be thought of as encoding these kind of products. And then, as Yvain mentioned as well, you extend the for now smooth noise to this collection of objects, which you then call a model. And that model maps these trees to the concrete space-time distributions that they're actually meant to represent. And at the level of the smooth noise and the canonical model, this is actually done in a multiplicative fashion. So you can already see that the problem if you send epsilon to 0 will be that then you would have to give meaning to these kind of products. But I'll get to that in a bit. And then there is, as Yvain mentioned, there is this base point here, which means that it's kind of a local description at the space-time point x. So for me, x in accordance with Yvain's paper is always a space-time point. And as Yvain explained, then there is you would have to do these kind of subtractions. And in this example, it's very simple, but they can of course get very, very complicated, especially in the most general setting. And then based on this model, of course, you have now a sort of collection of abstract Taylor monomials. And so you build a space of model distributions, which are basically expansions in these Taylor polynomials. And then you have an abstract version, namely this one here, of the equation that is printed at the top here. And now, actually, in this most general setting, one of the main results of this paper by Yvain and co-authors that I mentioned before is that you can actually give a very nice explicit formula as to what the solution to this abstract version of your concrete equation really is. But then, of course, you have to go back to the setting that you started out with, namely the equation at the top here, and that is done by the reconstruction operator. So you take your abstract kind of Taylor expansion of the noise that Yvain mentioned, and you apply the reconstruction operator, and you go back to what you started out with, this u epsilon. And if epsilon is actually positive, then we just get back what we know, right? So that means that the theory really can deal with what we have previously known. But then the problem, as I mentioned a little bit, is of course that if you send epsilon to 0, then the limit either does not exist, or sometimes it's I don't know, 0 or plus infinity, which is due to the ill-defined products. And so that's where renormalization steps into the game, and where really Yvain's work sits. So what you do is on this second level here, so on the level of the model, you let the renormalization group act. So you have this kind of new model here, which there are some maps M that act on the model space. And you define, and this is really a definition here, you have this U hat epsilon, which is the reconstruction of this guy here with respect to your new renormalized model. And so then as a kind of what is true in regularity structure is if you take U as we have just seen, and epsilon is actually bigger than 0, so you're talking about smooth functions, then you can actually write down, there's a set missing here, I think. Then you actually have an identity as to what your reconstruction operator does. So it's really the point is here always the same. And then in order to figure out what the renormalized equation actually is, what one would like to have such an identity that I printed here. So the pi's are now bold pi's, so there's no reference to a spacetime point. So basically think of just the model without subtracting these Taylor polynomials. And that is needed, as Yvain pointed out, in order to calculate the equation that the renormalized guy actually satisfies. And so that's a very complicated problem. And in the translation invariant case, there's all sorts of things that you need to introduce. You need extended decorations. There's many complicated things that you have to do. But in the non-translation invariant case, as Yvain mentioned, if you try to naively adapt the setting that already is very complicated, and you have some space dependent map M epsilon, then this is bound to fail. And the reason for that is that you need the renormalization does not only happen at the root, but if you have these non-translation invariant kernels, you have some internal products that need to be renormalized. And if you only do that at one fixed point, that is of course not going to work. And so there is a remedy that Yvain and Ismael found. That's this concept of the preparation maps. And what is particularly nice about them, and I'm going to comment a little bit more on the features and the still open problems, is that you really have the same algebraic structure. Also, you do have some state space dependence. And what I'm actually not going to mention, and Yvain sketched this as well, using the framework of this very nice review paper by Bailleul and Hoshino, you can use the heat calculus to show that the non-translation invariant kernel actually fits into the theory, to the assumptions, satisfies the assumptions proposed by the theory of regularity structures. So that's the analytic side. But so these state space dependent preparation maps are actually, just as a recap, defined here. I think Yvain only printed the ones where you don't have state space dependence. But as you mentioned, it's really the same kind of definition, only that you do have now this state space dependence here, and then of course these kind of prefactors that you have with these correction trees here, they actually do depend now on the state space as well, and they are renormalization functions because you don't have translation invariance anymore. And then there is some algebraic properties that you need to satisfy, basically this relation, so that for the experts that you want these maps to commute with your recentering operators. And then there's another crucial algebraic identity with respect to this product that Yvain and Dominique Manchon introduced if you want to have a strong preparation map. So that has been mentioned by Yvain. And so let me quickly run through what I think is the merits of this approach, of the strong preparation maps, and also possibly point to some open problems that have also been sketched. So the strong preparation maps, they have very nice algebraic properties. For example, they act as a right morphism property, which is very crucial in this one page proof that Yvain mentioned. And they also induce good multi-prelee morphisms. So if you're given this strong preparation map, you can actually build a good multi-prelee morphism from it. But what is still open is if the correspondence is one-to-one, like for example, in the case of branch graph path. And another particularly nice thing about them is you can really connect them back to what you had already known, what the theory, what the theory proposed. So if you have there's a kind of canonical construction. So if you have your strong preparation map, then you can build 2 new models. I denoted them here by C. Really just think of them as being the pi and then some recentering operators. So they are basically the pi. And you have this very nice identity here where you can see, and that's why I actually highlighted it. The construction is set up in such a way that actually here you don't see an x, so it's not the base point, but it's really the point that you're considering at the moment. So it's really this point here. And the nice thing about that is that this map pi tilde, I think Yvain denoted it by pi hat, so I apologize for that, is actually multiplicative. And so if you have this model distribution, this abstract sort of Taylor expansion in this model, then you can actually really write down what the reconstruction operator with respect to that model that you built from this strong preparation map does. And that's exactly printed here on the right-hand side, where really this X is all the same. So that's really what Yvain referred to as everything being completely local. And now if you have say a smooth noise, so say for example this that has been previously denoted by psi epsilon, then you can really figure out in this very concrete manner what the equation that what the reconstruction of your model distribution satisfies as an equation. And as Yvain mentioned, there's of course a very important example, which is this BPHC renormalization, which has been introduced in this by now well-known paper of Yvain and Martin Heyer and Lorenzo Zambotti, where you build your strong preparation maps from a character, and that character can actually now be dependent on the state space. And what is still open, as Yvain mentioned, is the convergence of the model. So then what you would want to do is you would want to send epsilon to 0. And if there is no state space dependence, so if you have an elliptic operator with constant coefficients, then this is done in a very general fashion in the paper by A.J. Chandra and Martin Heyer. But now, since you do have these renormalization functions and this state space due to the state space dependence, it's not clear whether you would have convergence, even though there's strong belief, as Yvain mentioned, that one can adapt the proof and maybe even simplify it by using this recursive structure that these strong preparation maps have. And so I hope that was a good overview of this very nice work by Yvain. And I want to conclude with some questions. And the first question, so I apologize to those who are more algebraically minded than I am, is about this one-to-one correspondence with good multi-Preeley morphisms. And I just, when I was reading the paper, I was wondering what would actually the impact of that be, the impact of that for the theory of regularity structure. So say you can prove that all good multi-Preeley morphisms do or do not induce strong preparation maps. So what would be the consequence or the impact of that? And the last question I had concerns the last remark in the second paper, so the locality paper. And that remark states that as opposed to the case where you have where you are translation invariant, it's not possible to find a very nice representation as you have in the translation invariant case, in the non-translation invariant case. So such an explicit representation is not presently known, even though some identities are presented in that remark. And I was curious whether there's actually some hope of identifying an underlying structure which is similar to the one that one knows for the translation invariant setting. So that would be the two questions. And yeah, I thank you very much for your attention, and Yvain for your very nice talk. Thank you very much.